Welcome back to WHS Study Guide Biology. My name is Jason Jewick, and where I would normally have an intro, I wrote this script really late at night, so I'm tired and cut me some slack. Just cut to the intro. Now we'll be following through with the Clash of Clans analogy I used in the previous episode. Now in Clash of Clans, the amount of resources you have correlates with the structures you can build and what types of structures you can build. In a similar way, the availability of energy in an ecosystem affects the size and diversity of the ecosystem. Generally speaking, larger ecosystems and more diverse ecosystems have more energy available. We call this production of energy gross primary productivity. But more typically, ecologists look for net primary productivity, which is the total amount of energy available in an ecosystem to be used in the form of biomass, which is all the organic material. To get net primary productivity, you subtract the rate of cellular respiration from the rate of photosynthesis. Back to the Clash of Clans analogy, that would be like the amount of resources you have left after you spend some of it on building your military and building your defenses. So speaking of the military in Clash of Clans, it's very similar to the consumers in the ecosystem, or heterotrophs. So the first level of heterotrophs, or primary consumers, are typically herbivores and will eat plant matter exclusively. At the next level up are secondary consumers, which will eat the primary consumers. So these are carnivores, which eat meat. Typically, however, ecosystems don't go beyond tertiary consumers, which are the third level up. It's important to note that this cannot be done because the amount of energy available at that point is very minimal and it's not really efficient to pass it on. Also note that omnivores can fall almost anywhere on here since they eat both plant and meat matter. So for the last stop, beyond tertiary consumers are decomposers. Decomposers consume everything, so fear the mushrooms! Okay, no, but for real, decomposers are the last stop for the flow of energy in an ecosystem. This is This is because the amount of energy decreases almost exponentially between each level. So you start with 100% at plants, then the first primary consumers would only get 10%, then 1%, then 0.1%, and so on and so forth. So the amount of energy is pretty much negligible. However, decomposers can interject anywhere because they decompose any dead organic matter, and they return that energy to the environment. So far we've discussed everything within the context of food chain, but there are other ways of describing the path of energy through an ecosystem, such as a food web. Now, a food web shows the multiple different ways to interconnect communities in the ecosystem and how energy flows between them through consumption. Another way to represent this is a food pyramid. A food pyramid places the organisms with the most energy at the bottom, all the way going to the very top of tertiary consumers. So that puts plant matter and vegetation at the bottom, and the tertiary consumers, like humans, at the top. So number pyramids represent the amount of organisms at each level. However, bear in mind this won't always create a pyramid, because you could have 2 trees support dozens of squirrels, so you would have, going from smallest to largest in that case. So it would be kind of like an upside down pyramid. However, you could also use a biomass pyramid. But once again, I must say, this is kind of like a step pyramid than really just a smooth one, because the 2 trees would have a lot more biomass or organic material than the dozens of squirrels they support. And with that, we move on to population ecology. So these squirrels which live in the trees would show clumped distribution because they live within a relatively small area but with high population. Other organisms display clumped distribution as well, such as sheep and fish, typically to stay safe from predators, or for social reasons like humans. We stay clumped close together in cities and things like that. Another reason for clumping would be for resources like food or water. Other types of distribution include uniform distribution and random distribution. Now, uniform distribution can be common in plant species where they each need a certain amount of room around them to grow, or in man-made environments where we plant trees and orchards in a certain pattern. And the last type of distribution, random, is actually pretty rare, but it's common among predator species such as lynx, cougars, who all hunt alone. So they have pretty random distribution throughout an area. The population density also ties into survivorship curves, or diagrams that show the amount of remaining living organisms over time after a measured set of births. So survivorship curves can be used to describe the reproductive strategy of a species. Type 3 species, which typically include insects and amphibians, have high birth rates but also high infant mortality rates. These species mature quickly with little to no adult supervision or care, and they also experience exponential growth when times are good. But when unstable environments occur, they just have a bunch of offspring, but not many of them live to adulthood. Organisms who fall into the type 2 survivorship curve often experience the same probability of dying all throughout their lives. These include mice and birds. Type 1 survivorship is common to species like mammals, in particular humans. We have very low rate of offspring, but these have very low also infant mortality rates, at least compared to other species. So as time goes on, type 1 species gradually die out, usually by age or disease. So if there's some factors you want to remember when trying to categorize a species as either type 1, type 2, or type 3 survivorship, there are some key factors you want to remember. You want to remember the birth rate, mortality rate, the life expectancy, and age structure, which is the distribution of ages through individuals in a population. Another important graph that you'll want to remember is population growth. Now, population growth is typically slow in the beginning because of low population and low reproduction rate. But as time goes on, populations will experience exponential growth, a time where there's abundant resources and offspring are plentiful. But as time goes on once more, logistic growth sets in. Now, logistic growth is caused by limiting factors on a population's size because the environment can't support all of them. Limiting factors are density dependent and density independent. Our density dependent factors include predation, parasitism, starvation because there's not enough food to go around, and things like that. Density independent are things like weather, extreme weather like hurricanes or fires, etc., or humans. We tend to mess with species a lot even if they would have done fine without us. So another important density dependent factor to consider is competition. Competition occurs when there's too many organisms fighting for a limited resource, and it can result in three things. It can result in competitive exclusion, it can result in character displacement, and it can result in resource partitioning. So competitive exclusion is when either species is reduced in numbers because of the competition, or one species is completely removed. Character displacement is one species like movement to a different niche as a result of not being able to take over the niche that they were competing for. And resource partitioning is when the two species just decide to use different parts of the same resource as to not compete with each other directly. One important example of this is probably ground squirrels or chipmunks. Chipmunks probably evolved from tree squirrels, but found that they were not able to climb as well as their brethren, and decided to instead use resources found at the roots of trees. So that means, from a biodiversity standpoint, competition is a good thing. It can result in more species richness, or the number of species, or the different types of species in an ecosystem. However, this will not always lead to species evenness, or the relative number of the different species in an area. Typically, ecosystems closer to the equator will have higher species evenness than ecosystems closer to the poles. This is because of the recent ice age, which makes ecosystems at more extreme latitudes actually newer than the ones at equators. Other factors that affect biodiversity include the species area effect, predator numbers, disturbances, and an ecosystem's ability to be stable, or stability. So the species area effect states that over a larger area, you'll find more species richness, typically because larger areas have more habitats, and more habitats can support different types of species. The predator numbers, that affects biodiversity, because predators typically, if they hunt two competing species that are fighting for the same niche, they keep both species down. With their numbers reduced, there isn't as much competitive exclusion between the two prey species. Now, disturbances are events that can change communities, typically by adding or removing organisms, or by altering resource availability. Note that I said adding organisms. Invasive species can be a huge disturbance within an ecosystem. Take Australia, for example. In Australia, they have a huge bunny problem that costs the government hundreds of millions of dollars every year. You see, Australia does not naturally have bunnies. They are imported by English settlers as hunting game. But what happened was, because there are no natural predators to the bunnies on Australia, they quickly overpopulated it and took up much of the island's natural resources, leaving very little for natural and native species. The reverse of this is stability, or an ecosystem's tendency to maintain relatively constant conditions. Now, most of the time, stability is dependent on one species which has an unusually large effect on its ecosystem. These species are called keystone species. One of the keystone species are sea lions, which help maintain prey populations within the coastlines of California. However, you should also know that communities can change over time. So this can occur by succession, which is a set of biotic changes that can regenerate damaged ecosystems or give rise to new ones. Primary succession is when a damaged ecosystem forms a new one. This is typically done by pioneering species like fungi and other small plants like ferns, which can help break down rock sediment into soil to help give rise to a new ecosystem. Other than primary succession, we also have secondary succession, which is the replacement of a species that was removed from an ecosystem or by damaged ecosystem. This is typically characterized by pre-existing soil and pre-existing species and communities, unlike primary succession. And with that, we finish up ecology and pretty much when high school study guide biology. I might finish up with anatomy, but this will probably be the last episode that you'll see before comps start. My name is Jason Jewick, and this has been Whitney High School Study Guide, but where did all these invasive species get here? No, but for real guys, thanks for watching Whitney High School Study Guide Biology. This will probably be the last episode before comps because we won't have time to film another one. However, we will continue in the summer and we hope for you guys' support. And we'll probably be filming next year as well. So, hope to see you then. This is Jason Jewick, signing off.
And Joker.
Please donate to save our souls. We're all dead on the inside now.